We begin the study of calculus with the concept of limits. And we can see, as I've written here, we're going to look at limits in a couple of different ways, in several different ways. And so this is going to be part one of that discussion. And you can see here that we're beginning with a function f of x is equal to 2x plus 1. We read in terms of limits, the notation we see here on the left-hand side is when we're just referring to the function f of x, but we can look at what we're doing on the right-hand side as well. And it says the same thing, except it's using the expression that f of x is equal to. We read the first one as the limit of f of x as x approaches 3 is equal to 7. Now, while we're here, let me make a discussion a bit, is that the 3 value in either one of these is called the target. And what the limit is equal to, the number, is the limit value. Now, we need to understand what this is asking for, and let's just, that's the discussion here, is this is asking us for what value is 2x plus 1, or f of x, what value is 2x plus 1 getting near as x gets near 3. So let me write that down. Let's write it this way. The limit of 2x plus 1 as x approaches 3 equals, well, when we ask this question, let's put it this way, when we ask this question, we're asking what value is 2x plus 1 getting infinitely close to? As x gets infinitely close to the value 3. Now, understand, we're not asking what is the value of 2x plus 1 equal to when x is equal to 3. But that seems kind of like what we're asking here. So let's go back up to this expression that we see here. And once again, let's just think about this. As the value x gets closer and closer to 3, then of course 2x plus 1 is getting, 2x is getting closer and closer to the number 6. It's not actually equal to 6, but it's very, very close to 6 when x is very, very close to 3. And when we take that number that's very, very close to 6 and add 1 to it, we're very, very close to 7. And that's what we mean by the limit. As x gets very, 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 very close to 3, what is 2x plus 1 getting very, very, very close to? And I'm going to make a point once again. I know this seems like a repetitive, but we're asking for the value of 2x plus 1, what 2x plus 1 is getting close to as x gets close to 3. And in this case, without actually being equal to 3. And that won't make sense yet, but we'll see in a moment that that does make sense. Okay, without being equal to 3. Now, once again, that's called the 3 is called the target value. And generally, we see a question like this: what is the limit of f of x as x gets near some number a? And of course, we're wanting to know then what value f of x gets close to as x gets nearer and more near to a. And let's pause here, and on the next page I'll talk about the different ways that we can find the values of these limits. Although it seems elementary in this problem, we'll see that it will become more difficult as we go through. Okay, here we're going to discuss the 3 different ways to find a limit. And I've listed them in order from least desirable to most desirable. So first you see that we can find a limit numerically, which really means we're going to be guessing. And the way we do this is we create a table of values. And that's the first thing that we'll see how that works in our first example. So we do this by creating a table of values. And like I said, this method generally is unreliable. Maybe for the problems we see, it's not a big deal. But if you're working on more complicated problems, we're really just making a guess in these cases. The second method, as you see listed here, is we can find a limit graphically. And that really means that we're going to look at a graph and make the decision. Now this works real well when the graph is already there for us to look at. If we're having to create the graph, of course, that makes it more difficult. The third method I've written as analytically, and in this method we use algebraic techniques. We basically use mathematics rather than using a guessing method or a graphical method. We're actually using algebraic methods to calculate the value of the limit. And that's what we're going to really be most interested in the long run. Well, as I said, we're going to first investigate the numeric method or the table method. And so we'll look at the very first problem that we saw a moment ago when we found out that the value of the limit was 7. So here's the question once again. Find the limit of f of x, which is equal to 2x plus 1, as x approaches 3. And of course, the way that would normally be written, once again, is a limit of f of x, as x approaches 3. Use a table. So this is the way that works. We're going to create a table that is horizontal in nature. First, I'm putting a vertical line here to separate our values. So I'm going to create this table. On the first row, we'll have x values, and on the second row, we'll have corresponding f of x values or y values. Now, in the middle of this table, on the x value side, we're going to have the target number, the 3. And of course, that's the same 3 that we see right here. Now, remember, that's called the target. So the idea is we're going to create positions in here. Let's see, on the left side of 3, maybe we'll choose 3 x's, and maybe on the right side of 3, we'll choose 3 x's. So I'm making a spot for each of those values. And the whole idea is we're going to choose x's that are smaller than 3, but getting close to 3, and we're also going to choose x's that are larger than 3, but getting closer to 3. And so, for instance, I might start out with an x value of, let's say, 2.5. Okay, well, that's not 3, but as I get closer to 3, I might choose an x value of 2.9, for instance. And then I might choose, again, an x value of 2.99. And you can see my x values are going from smaller to bigger from the left-hand side, getting closer and closer to 3. Now, on the right-hand side, I'm going to go from bigger to smaller. So I might choose a 3.5, that's bigger than 3. And suppose I'm going to get closer to 3, I might choose a 3.1. And maybe I want to get even closer to 3, I might choose a 3.01. So I've chosen my x values there. And again, I'm letting these x values get more and more near 3 from the right-hand side. Now, the whole issue is we're looking to guess. See, we're looking to find the value that should be there. And the way we do that, that's the limit then we need to know what f of x is, or f of 2.5. And so we simply replace in our formula for f of x 2.5 every time we see an x. So it would look like 2 times 2.5 plus 1. Well, that would be 5 plus 1, or 6. So in our table, corresponding to the x of 2.5, we have an f of x of 6. Now we'll continue the same idea for 2.9. So for 2.9, we need to calculate the f of 2.9. So once again, we replace in our formula x with a 2.9. Well, 2 times 2.9 is 5.8. And then we're adding 1 to that, and so we get 6.8. So corresponding into our table, we have a 6.8 for f of x when x is 2.9. Likewise, for 2.99, we would calculate f of 2.99. And when we do, we would have 2 times 2.99 plus 1. Well, what is 2 times 2.99? Off the top of my head, I don't know, so I might have to come over here and do a calculation. So 2.99, of course, I might even have a calculator. 2 times 9 is 8, with 1 left over. 2 times 9 is 8 again, but 1 is left over. 2 times 2 is 4, so we actually get 5.98, don't we? So we end up with 5.98, but remember the plus 1. And so this ends up being 6.98, our f of x. So in this position, we see a 6.98. Now it appears that these f of x's are getting more near 7 as x gets more near 3. And it probably is a good guess at this position or at this time, but generally we need to see what's happening on the other side of 3 as well. So we'll substitute in a 3.5, that x value, and we'll go through the process as we did above. So f of 3.5 ends up being 7 plus 1, or 8. So we fill in this with 8. And you can understand that we'll continue that process. When we use a 3.1, we would end up calculating a 7.2. Would be our calculation, 7.2 for f of x. And when we use a 3.01, we would calculate a 7.02 for f of x. So you can see that on either side of 3, the f of x values are getting more and more near some number we're going to guess in the middle, and it looks like, of course, they're getting close to the number 7. Okay, and so from the conclusion from this table is that we would say, oh, okay, our guess is, or our conclusion is, the limit of 2x plus 1 as x approaches 3 is the number 7. And again, I understand that that almost seems silly in this problem, because we can just look at the function definition, 2x plus 1, and decide what we're getting close to. But the next problem will illustrate that we can't always do that by just substituting in. Okay, you can see the problem that we have here says use a table to calculate, or maybe we might say find actually, the limit of x squared minus x minus 6 divided by x minus 3 as x approaches 3. Now, once again, when we use a table, let me express to you that this method is really making a guess based on some numeric values. But for this problem, it will be a very reasonable guess. Now, you can see in the limit that we have here, the expression is much more complicated. And so we can't really tell what's happening, because as x gets near 3, the denominator is actually getting close to 0. And so it's hard to us imagine, we know we can't divide 0 into anything. Now remember, x isn't actually getting equal to 3, it's just getting near 3, closer and closer to 3. So this fraction will never have a 0 in the denominator, but we still want to know what number this fraction is getting close to as x gets closer to the number 3. And so we have to have another method by just imagining what that number is here. So we begin building the table in a similar fashion to what we did a moment ago. On top we'll have x's, and on the bottom we'll have values that are f of x. And of course, to make the table, we'll draw this line in between. And remember, in the middle of the table, we'll have the target number, and in this case, again, the target number is 3. So in the middle of the table someplace here, we put the target, and once again, that comes from the 3 that's right there. Okay, so I think I'll do as we did before. I think I'll choose 3 numbers smaller than 3 and 3 numbers larger than 3 for our x values. Okay, and I think I'll start out with a 2.9 as a number smaller than 3, and then I'll choose a 2.99 as a number smaller than 3, although I'm getting closer to 3 each time. And then finally a 2.999. Now on the right side of 3, the positive side of 3, I'll start out way out here with a 3.1, and then I'll get closer by using a 3.01, and I'll get even closer yet by using a 3.001. Now, so remember what is going on when we do this. For the x value, for instance, 2.9, we're going to find the f of x value that corresponds to that. And that means we have to put in 2.9 for x in the expression. So we'll have a 2.9 squared minus a 2.9 minus a 6, all divided by 2.9 minus a 3. Of course, like I said, x is getting close to 3, but it's not, but it's not 3. So in this case, x is 2.9, so we don't have a 0 denominator. Now, I'll be honest with you here, I used my calculator, as I would probably expect you to do, and I did the calculations and got a value of 4.9. So I fill in this table position with a 4.9. And next I chose the x value of 2.99, and so I'm going in to calculate f of 2.99, and you understand what we're doing here. Whoops, there was a square way up here that I left off. So as I'm calculating f of 2.99, I have to square it and subtract 2.99, and then subtract a 6, and then I have a 2.99 and subtract a 3. And this time when I use my calculator, I got 4.99 as my result. So in the table in this position, I put in a 4.99. Now just as I pause here, remember, we're trying to decide what number these f of x's are getting close to that would correspond to the value 3 for x. And we may not be quite sure what's going to happen, but in this case, we'll see the pattern as it emerges. Now, I'm not going to bore you with the rest of these calculations. Let me just tell you that when I use 2.999 right here, I calculated my f of x value to be 4.999. And when I came out here with the 3.1, I calculated the f of x to be 5.1. And then for here, 3.01, I calculated the f of x to be 5.01. And then here I calculated the f of x to be 5.001. And so let's understand what's happening. We're letting the x's get closer and closer to 3 from the left-hand side, and then we look to see what's happening to the f of x's. And they seem to be getting larger and close to number 5. But we need to verify that by looking on the right-hand side. So if we're on the right-hand side of 3, and we're letting the x's get closer and closer to 3, we look at the pattern of f of x's, and that pattern is also getting closer and closer to the number 5. And so with a reasonable amount of certainty here, we're guessing that we're getting closer and closer to that number 3. And so that's actually the limit value. So our conclusion then, we would conclude in this case that the limit of x squared minus x minus 6 divided by x minus 3 as x approaches 3 is equal to the number 5. And we found that by the use of the table, and we couldn't do that by substitution. you change directions a bit for the next problem or the next example, we're going to deal with the same function as you see. We're asked to calculate the limit of f of x as x approaches 3, where f of x is equal to x squared minus x minus 6 over x minus 3, which is what we built a table for a moment ago. But this time we're going to use a graph to make this determination. So we're using a graph to do this. Then normally when we're asked to use a graph, the graph is provided for us. But we're going to go through the exercise of creating a graph for this function, and then we'll worry about determining the limit. So our first task is to graph the function f of x is equal to x squared minus x minus 6 over x minus 3. And although it doesn't say so, we recognize that x cannot be equal to 3, otherwise we would have a denominator of 0. So we can use any x but 3, and so our graph is not going to have a point for x equal 3. Now, let's look at this numerator. In this specific case, I think the numerator, x squared minus x minus 6, can actually be factored. I think if we analyze that, we'll decide that that's x minus 3 times x plus 2. And the denominator is x minus 3. Now, we have to be a little bit careful, but we recognize, here's the question. We recognize that we can cancel this x minus 3 in the numerator denominator and be left with just x plus 2. And so the question would be, is this f of x equal x plus 2 the same thing as f of x equal to this fraction? That means, do we get the same y values when we choose the same x values? And we do, as long as x is not 3. In the original function, we can't use 3, and of course there doesn't seem to be a restriction on x plus 2. But the original function requires that we can't use 3, and so we have to keep that in mind as we make this graph. But then we recognize f of x equal x plus 2 is just a line when we graph it. But we're going to have a line that doesn't use all x's. We're going to have a line that has a hole at it where x is equal to 3. So since we know that we're actually graphing something that looks like y equal x plus 3, we can simply create a solutions table for it with just 2 or 3 points, and then plot those points and get our graph. So we choose x to be 0, we'd see that y is 0 plus 3, or simply 3. If we choose x to be 1, we would calculate y to be, I made a mistake. Y is equal to x plus 2, not x plus 3. And so in this case, we would actually have y is 2, or the point 0, 2. Now on the other hand, if we choose x to be 1, we would calculate y to be 3. And we choose x to be 2, we would calculate y to be 4. But remember, we can't choose x to be 3. That's not allowed. Well, let's plot the points we have. 0, 2 would be this point, and 1, 3 would be this point, and 2, 4 would be this point, and we could choose more points, but let's do remember, let me do this, not that this would be part of our graph, but let's remember that since x can't be 3, then where the line is going through this position, that point can't be on the graph. So as we're drawing our line, we see that, remember it's a line, as we're drawing a line, we know we'll have part of the line here, and we'll have part of the line here, but as we are at this position, that line cannot use the x value of 3. And so that's the idea that we have a line that has a hole in it at this position. There's a hole right there. I've made it a big hole, but it's an infinitely small, of course. Okay, now the job we're faced with is to calculate the limit of f of x as x approaches 3. And the first thing to recognize about this when we're looking at a graph is f of x just means y, doesn't it? See, that means y. So the question that's being asked here is, what is y getting close to? as x gets close to 3. That's really what the question ends up being here. And so here's the way we analyze this. We think about the x values, and we'll think about x values that are to the left of 3, but getting close to 3. So we're taking x values that maybe are starting over here, and they're getting closer and closer to 3 without ever being equal to 3. Now these x values generate positions on the graph. And so maybe an x value that's here will generate a position on the graph that's right there. And of course that is a y that is in this position. But as these x's are going in this direction, then we're talking about points that are on the graph or on the line going in this direction. So we're plotting along in this direction. And as we do, then the y's that go with this point, these points are going up this way, aren't they? Each of those y's are going further and further up. And I still have let me make that real clear about what's happening there. Now, on the other hand, if we choose x's that are bigger than 3, but getting close to 3 from the right-hand side, then we're on the graph in this position, and we're moving along in this direction along the graph that go with those points. So now we're talking about y's over here that are moving downward. And so the question ends up being, as x gets close to 3 from either the left or the right, our points are moving to this position that's not actually on the graph. But what we want to know is what's the y value of that position. See, what's the y value of this position that the graph is getting close to? And the y value of that position is this 5, isn't it? See, that's that y value. So as x's get close to 3, either this way or this way, then the y's are moving up the graph because we're going this direction or this direction toward this position. So the y's are moving here, they're moving here, they're getting close to that y value. So for that reason, we can say the limit of f of x, as x approaches 3 in this case, is 5. So on this page, I want to continue this idea of finding limits by using a graph. And this time we won't really know what the function is. We just see a graph of the function. And so this is going to be a little more general than what we've done in the past. But let's see if I can draw us a function here. I mean, the graph of the function. So let me get the graph going. Okay, so of course here's the x-axis and here's the y-axis. And suppose here is -1 and here is +1 and here is +2. Let's say here's -2. Sorry, I'm jumping all around, and here's -3. And I don't really need to label this x-axis. I'm just going to suppose that we have some value on the x-axis that is a. So this is where the a value is. And I don't know what that number is, but it's just some value of a. And let's suppose the graph of f looks something like this. And we get to here, and right here where x is a, okay, and then it moves up like this, okay. So this is the graph of f of x. And the question we're being asked now is to find the limit of f of x as x approaches this target number a. So we don't even know what a is, but that doesn't matter. Okay, now a couple of things I want you to notice before we do this calculation. Notice that f of a is undefined. See, there's not a value of y when x is equal to a. So this is an important concept right now to find out that in this case we have that situation that f of a itself is not defined. Now, let's get back to this question of what is the limit of f of x as x approaches a. And again, what we're needing to recognize is that as our x's get close to A, and they can get close to A, and they need to get close to A from either the left or the right, I mean both together. When they're getting close to A from the left, then we're traveling on the graph in this direction, aren't we? And when we get close to A coming from the right-hand side, then the points are traveling along the graph in this direction. And so the question is where are we headed when we move close to A for X? Well, we're headed to that position. And we're really wanting to know the Y of the place we're headed. Although that point's not there, we're headed to that position, and the Y value of that position is -2. So we can say that the limit of f of x as x approaches A, in this case, is the number -2. In other words, when x's get close to A, then our y's are getting close to -2. And again, it's important to recognize that the limit exists here, although there's a hole in the graph at that position. And it's not what the value of the graph is at A, it's what the value is getting close to. And so that's really the only thing that we're concerned about here. So the function can be undefined at A, but we can still have a limit as x approaches A. Okay, let's look at the next example, which will be a little bit of a variation of this idea. So let's see if we can come up with another graph here. Here's our x-axis, of course, and here's our y-axis. Let's say this is 1, 2, 3, 4, and this time, let's say A is about here again. And our graph looks a little different this time. There's actually going to be a hole in our graph at this position, and the function's coming down like this maybe, and it's hitting this point, and then maybe it comes down here and goes off again, okay? And something's a little different here. Let's say that actually this point is on the graph, okay? So there's a hole in the graph as we move along the graph, but there's also a position, a value defined. And so let's note in this case, this is an important note for later on, that in this case, f of A is actually the number 3. See, the value of y when x is A, the value of y is actually the 3 right there. And in the example before, the function was completely undefined. But it is defined here, it's just defined in a strange way. So the question now we're asking is, what is the limit of f of x as x approaches A? And the hardest thing to get used to in calculus is that we don't let things like this keep us from the main idea. Because it's not what's the value of f when x is A, it's what is the function getting close to. What is y getting close to as our x is near A. And as our x is near A, our graph is moving in like this from the left, or it's moving in like this from the right. And so we're moving into this position where there's a hole. But the position of that y value is 1. So y's are getting close to 1 when x's are getting close to A. And this top point didn't really play into that, did it? Although it seems like it should, the answer here is actually 1. Our y's with these points are getting close to 1, although that point's not on the graph. Okay, so a note of this. Let me pause. In this last example that we're going to do about determining the limit based on a graph, once again we have the graph of this function f of x. And of course you can see that this graph doesn't just have a hole in it, it's completely broken. That the two parts of the graph are separated. Now notice the point that we have here that I'm making a point of. This point's on the graph, but the point up here associated with A is not on the graph. So A comma 2, x is A, x is a, and y is 2, is on the graph. When x is a, y is 2, not 4, which would be up above. Now, in this case, the limit of f of x as x approaches a does not exist. I'm going to explain why here in just a moment, but we need to recognize the situation. In this case, the limit does not exist. Now, here's the issue. When we're discussing the limit of f of x as x approaches a, we want to know what single y value we're getting near when x is near a. And it doesn't matter whether x is near a on the left side or x is near a on the right side. If x is near a, then what is y near? And we have an issue here when the graph is broken. So you can imagine that when we let x get near a from the left-hand side, we're traveling along the graph on this part of the graph, aren't we? And as we travel along the graph, when x gets near a, we're of course getting close to this dark point. And so y is getting close to 2 in the case that we get close to a. So when we're close to a in here, then the y's are close to 2, aren't they? On the other hand, if we get close to a from the right-hand side, we're moving along the graph up here. As we move along the graph here, the y values we're getting close to are associated with the y value of that blank spot. And so in this case, we're getting close to 4. So there's no certainty. We can't say when we're close to a for x, is our y close to 2 or is our y close to 4? Well, it just depends. We can't say with certainty unless we know more. And so, since we can't say that y is close to 2, or we can't say y is close to 4, because it depends on what x's we're using, then in that case we say the limit does not exist. We're not getting close to a single number. Now, it does lead us to another concept, and that's the concept of a one-sided limit. Okay, we can have one-sided limits. In this case, the limit does not exist, but we can have what's called a left-sided. When we say one-sided, we can have a left-sided limit, and we can also have what's called a right-sided limit. Limit. Now, here's the way we would ask for a left-sided limit. Okay, here's a left side. This is what it would look like if the question was asking us for a left-sided limit. We would say, find the limit of f of x as x approaches a, and the way we say left-sided is we put a minus sign that looks kind of like an exponent on a. And that means we're getting close to a from the negative side. And of course, the negative side of a is the left side of a. And so that's just asking us, as we stay on the left side of a, but we get close to a, then what is our function, what is our y value getting close to? So we're referring to getting close to a from this side. And as we refer getting close to a from this side, we can see that our y values are getting close to 2 up here. So in this case, we'd say the left-sided limit is in fact 2. On the other hand, the right-sided limit, when we would ask for a right-sided limit, it would look almost the same. We'd say find the limit of f of x as x approaches a, and when we want to say right side, we mean from the positive side of a. So we put a little plus sign that looks like an exponent. And that just means we're getting close to a from the positive side. Positive side meaning the right side. So that means we're getting close to a from the right side, which would mean, once again, we're traveling on the graph in this direction. And when we travel along the graph in this direction, then the y we're getting close to, of course, is the y value of 4 appears. So the right-sided limit is actually 4. Yes, actually 4. So that's the idea of left-sided and right-sided, and also the idea that sometimes a limit does not exist. Because in fact, for a limit to exist, I can make a point of that, for a limit to exist, not a sided limit, okay? For a limit to exist, then both the left-sided and right-sided limits must be the same. For a limit to exist, then both the left-sided and right-sided limits must be the same value. And as you can see, that means we're getting close to the same number on both from both the right and left sides. Must be the same. Okay, we're going to stop this part and start up the next part on in the next lesson. Still on limits, but we're going to talk about calculating limits analytically.